videos, drop a like and a comment saying thanks. This is 1503, last moment before all ants fall out of a plank. Quick video today. This is one of those problems where knowing the trick, right? Knowing some information, a hint, something that isn't completely obvious, which perhaps could be derivable from solving a few examples, but it's not something that's immediately obvious, is really the major assist, which will provide you with the means to find the solution to this problem. So let's go ahead and get right into it and just understand that if you don't know the solution and someone else might find it faster, it's not necessarily that they're more intelligent than you. They may have just seen this trick before and used it, and that's what led them to something that may not be completely intuitive to you. All right, so let's go ahead and get right in. We have the wooden plank of length n units. All right, so there's this wooden plank, and it's n units long, okay? So if we draw this plank out, right, I'm gonna draw a little plank on my screen here, and this thing has n units. So what that means is that the length of this thing is n, right? So whatever n is, which is provided, that is the length of this corresponding plank, okay? Some ants are walking on the plank. Each ant moves with a speed of 1 unit per second. Some of the ants move to the left and others move to the right. Okay, so there's ants on this plank and, well, they're moving to the left and they're moving to the right. And if they're on a plank, what does that kind of imply? What's the implication? What are you insinuating? Well, the ant's going to fall off, right? If a little ant, let's draw a little ant. I'm going to do my best at drawing an ant. You guys are going to be so impressed by this. Does that look like an ant? This little ant is here, right? This ant is over here, starts on the plank somewhere, and then the ant starts moving, right? Boom, 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 boom. And eventually this ant's going to reach the end of the system, and it's going to, whoa, it's going to fall off. Boop. Okay. It's insane how slow the delay is on my computer. All right, but that's neither here or there. When two ants are moving in two different directions, meeting at some point, they change their directions and continue moving again, assuming changing directions does not take any additional time, okay? When an ant reaches one end of a plank at time t, it falls off the plank immediately. Like I said, right? So if an ant's here and it starts moving, it could fall off the plank and sayonara. Given an integer n and two integers are raised left and right, the position of the ants moving to the left and the right remove the movement when the last ant falls off the plank. So I'm not going to draw this example because I feel like this is a pretty good graphic already, right? So in this example, we have ants going left that are at position 4 and 3. So that means that there's an ant at position 4 and an ant position 3 going left, right? And we have ants at position 0 and 1 going right. So that's kind of how this information is provided in this problem, right? You have n equals 4, so that's the length of the plank, right? It's 4 units width. And then you have the ants that start going to the left, you have the ants that start on the right, and then their positions, okay? And then you can just simulate through the problem, right? So this ant's gonna move to the left, this ant's gonna, directions. This ant's gonna move to the right, this ant's gonna move to the left, this ant's gonna move to the right, this ant's gonna move to the left. So this one moves left to here, this one moves right 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 to here. Now these two ants just hit each other, so now they're gonna bounce off each other. So B, which was once going right, is now gonna go left, right? So that's why it changes directions here. But then it's going to hit A at the next second here and bounce off. So now A is gonna be bouncing this way and D is gonna be bouncing this way. This is kind of hard to kind of try to simulate in my mind, but you can see that here, right? That when things are bounced, when they hit each other, they bounce off. It's a pretty complicated problem. And then the ants fall off, and at T5, so at T5, there's no more ants on the system, so we return 4. So we're trying to return, how long will there still be an ant on this table, right? On this plank. At what time will there be no more ants, right? What's the last second that there's ants on the table? And that's time 4 here, right? Okay, so this problem is kind of confusing because it's like, you could simulate the answer, right? You could simulate the answer and just, start the problem, go at each second, I look at all the ants on the board. If they look at their directions, if they intersect, if they collide, change their directions. If not, continue down the same direction. If they fall off, remove them from the board, right? And you could do that until you get to the end. The problem with that though is, well, you know, it could take a while, right? Like, I don't even know how to close the time because I don't know how long it would take, I guess. I do, but I mean, I guess I wouldn't using this. So, you know, what if it takes all of the number, the size n, right? Like, for example, if you had n ants going in one direction and you wanted to figure out how long there were ants on the board, well, then it's going to take n squared time, right? Because for each time slot, you have to simulate a run. So you have to simulate the positions of each ants. So then you have to determine where ant's going to be at the next time run. And that means that you could end up doing that n times. But for each of those n times, once you have to simulate the positions of the ants, you have to determine exactly where the ants are going to be. So you have to look at each board slot to determine where ants are going to be. So that could take n time as well. So you have to do n operations n times. It's n squared. N is 10 to the 4. 10 to the 4 squared is 10 to the 8. That's going to far exceed our time limit exceeded error. So we need to find some sort of alternative way of solving this that's not just a direct simulation, because a direct simulation will lead to a time limit exceeded issue. Okay. Now, what I'm going to do here, right, is I'm going to write this down again with our ants. Now I'm going to just use the letters, right? We have and we're going to notice something very interesting that is not always immediately recognizable. So I'm going to do it like they did it in between. So we have A, B, blank, C, and D. And then we'll draw our little plank here as well. And I apologize about the delay. I'm actually going to get a new computer some point here. So here's our plank like this. And then we'll just go through kind of how this works. So, you know, I said I wouldn't simulate it, and now I'm going to. Whatever. So what happens to A and B? So A is going to move one over, B is going to move one over, C is going to move one over, and D is going to move one over. All right, so A moves, B moves, C moves, D moves. And then we have A and B on top of each other. Right? And then C and D on top of each other. And then we have B and... I'm not going to do that. I changed my mind. There's a simpler way that we're going to do this. I'm not going to walk through this whole problem to get there. What I'm going to do is basically just show you what happens when you have two ants walking to each other on a plank. Okay. So let's say these two ants are walking towards each other on this plank, right? What does that end up looking like? Well, first, they just start running into each other, right? So they start here, then they go here, and then they hit each other right here, then they bounce off, right? So, you know, you can see here that they're starting to get closer. They hit each other and they bounce off. Remember, this is instantaneous. So this happens like that, and then they go on their merry way, right? Oh, they bounce off each other, right? So they bounce off, and then at this point, right, they drop off. So they bounce off each other, right? Now this will happen any general number of times. It could happen an infinite number of times depending on, you know, how many of these ants are on the plank, how many of these ants are falling off the plank, whatever, right? Like in this example, it's really convoluted. Like they're constantly hitting each other and bouncing off. And of course, eventually, if you change directions and go left, you're gonna fall off the grid. So there's no like infinite loop or anything, right? But all of these, you know, interactions are some combination of this thing occurring, right? This thing meaning, you know, you run into something and you bounce off it, right? But something that's interesting about this problem is, well, what if we didn't think about it being A or B? We just thought about it being a generic ant, right? If we thought about this being a generic ant, I'll use a X to represent just a generic ant. And what I mean by that is, what if we don't label the ants and we think about what happens when they bounce off each other, okay? So they're going to go, right? Right, so I have these two, they hit each other, then they bounce off. Right, so initially they were going like this, then they hit each other and bounce off, and then they fall off the map. Right. Now what's weird about this, what you'll notice is, well, this is equivalent to this one going that way, and this one going that way. Meaning what? You know, we can think of this as A bouncing off and B bouncing off, but an equivalent non-intuitive thing is, well, even though they bounce off each other, the paths are identical if they didn't bounce off each other, right? So what that basically means is, if you look at this, when things bounce off each other, it's equivalent as if they just went through each other and they switched bodies, right? This guy, A's initial intention was to go right in this example, right? A wants to go right. And A became B and continued going right. You could think of it that way, right? It's kind of weird. B's initial intention was to go left. And when it hit A, it didn't stop going left, right? It just became A and then continued going left. So if something starts at the right and it goes to the left, if it hits something, it just switches spots with that thing, but it continues the same path, right? As soon as B interacts with somebody, it's still going to continue going left. It's just going to change the ant that continues that path, right? So if you have a plank like this, right? I guess the point I'm trying to get to, and I apologize today for my poor video quality. It's just that I'm kind of frustrated because my computer is being exceptionally slow, and I'm utilizing a certain amount of the compute within my brain, focusing on the fact that there's a considerable delay, and I'm not focusing entirely on the topic at hand. So if you're wondering why maybe I seem a little what? Distant, well, that's the reason. So the point I'm trying to make, right? If you have this ant X and you have a board like this, okay? So you have an ant X and you have a board or a plank like such. Either X is going to go through the whole system until X falls off the board, right? Right at this point here. So either X is going to continue going until it falls off the board, or somebody else will interact with X, right? So either you continue down your path all the way off the board, and if wherever you're starting on, it's going to take you that much time to get to the end, or somebody interacts with you and that person ends up continuing your path. So that person will then just finish your path down the board if that's the case. Okay, so if you interact with somebody, well, then that person is just going to take the remainder of your load, right? But the amount of time it took is still the same, right? The amount of time associated with your initial path, either somebody else takes it or you continue it yourself. And that can happen any number of times, right? If then later somebody here at this side of the board came in, now I'm going to make this actually real complete here. Sorry about this, guys. I'm just really trying to make something that is obvious. Right? So if black is going down and pink hits it, well, then pink will just complete its path. And then if pink's going down and someone else hits it, well, then blue will just continue its path. Right? But what you'll notice is that the length of this path, starting from where the black X is the same no matter what. No matter how many times somebody hits this black node, it's going to continue being the same length, right? And that's kind of the beauty of this problem. So you can say, well, oh, this is a problem where, they're colliding and bouncing off each other, and that's going to affect how long it takes for someone to fall off the plank. But if you really look at it and you simulate an example, the collision is just going to affect which ant is going to end up taking that path. But the total length of time it takes for something to fall off the path is the same, right? The path contributed by this black X, although it becomes the pink X and then the blue X, it's still the same length of starting at this position and having to go across the entire plank, right? So then really what our problem is we have to look at how long it takes something, right? If something is going to the right, how long is it going to take? If something is going right, like this example here, if something is going right, how long will it take? Well, it's going to take the position of the thing going right and minus that, right? Because the thing is going right. So what I'm basically saying here is how long will it take for something to go right to fall off the board? Well, this thing starts at position 0, so it takes the length of the board to fall off, because there's going to be a node, either the node itself or the ant itself or someone else that ends up taking that path. So it's going to take the length of the plank minus the position of the element in order for whatever is associated with that path, it could be the ant itself, to fall off the board. Okay? And then to go left, well, how long is it going to take someone going left to fall off the board? Well, if they're going left, it's just their distance from the front of the board, right? If an ant is here, right, this ant here starts going left. So when it collides with another ant just ends up finishing its path. So it's just there's gonna be a path associated. Some ant, it could be the ant itself, is gonna be on the board going left, and then it's gonna fall off the board this many times, the length of how many, the L node, right? And another way you can think about it is just say, well, let's just imagine they don't collide, right? We can really frame this and say, well, since they kind of like cause one another to take each other's paths, we can just look at this problem and say that they don't collide at all. And we could just say this problem is equivalent, right? It's equivalent to just saying, you know what? This is actually the pink's path, right? And this is actually sorry, let's get this all right here. Right, this is actually the pink's path. And in reality, this is the black's path. And in reality, or in theory, right? In reality, it's different. And in reality, this is the blue's path. Even though the actual picture is different, right? And the actual picture is where, the black node bounces off this pink node, and this pink node bounces off the black node, then bounces off this blue node, and the blue node bounces off this pink node and goes to the right. But we can look at it as the same as just saying there's no collision, they just go right through each other, like very ghostly. And then that means that the length of their path, the amount of time it takes them to fall off the plank, is just their position. If they're going left, then it's their position from the left. If they're going right, it's their position from the right, which would be n minus position r. So then our solution would be just the max of both of these, right? The max of both of these. So the max of n minus position of r is the max of n minus the max of position of r. So that's just n, because n is a constant. So n minus the max, the same as plus the minimum. So plus the minimum of position of r. Is that right? Yeah. And then the max of position of L. All right, that's pretty ugly, but I'm going to just write it down here. So we can just say, okay, we want the max solution, right? We want the one that's going to take the most time. Well, either you're going from the left, so you want to see the one that's starting, going left, going right. You want the one that's starting to go right, right? Who's going right? Well, whoever's farthest left, it'll take them the most time to go right. Or we want the max from the right, which is, well, whoever's going right. Dude, my direction skills are really bad for some reason. Or the max going left, right? Which would be, you know, if you're going left, then if you're imagining a scenario where you're just going through, then whoever's the farthest right, will end up giving us the solution. Sorry, guys. I don't know what's going on with me today. Okay. Okay, so now we have empty argument scenarios. So to fix this, you know, this is just a little cheat, I guess. So we can have a default value. So what would the default value be here? So if we want to make this not be the solution, we would want to make n minus what? So float infinity. And then if it was max could be an issue here, we could do default equals float negative infinity. Because we want it to be as small as possible so that it's not chosen when there isn't a left or there isn't a right, right? Because there's cases where it's only going right, only going left, so then these mins or these maxes would be empty sequences, right? Okay, cool. So what's the run in space of this solution? Well, all right. So left is size, it's just the ones going left. So there can only be n going left at most and most n going right. So we can just look at it in terms of n. For space, well, that's pretty easy, right? Because we don't create anything. We just find maxes and mins, so that's constant space. Right? We don't even create any variables. And then for time, well, we have to look at all the right elements, and we have to look at all the left elements, and there could be at most n, right? So, well, actually, I don't know. Can theirs be stacked? I didn't look. They're all unique and they can only appear in one. So there can only, left plus right can at most be n. So for time, all the right operations to find the max or the min or whatever, right? To find the value we're looking for in right and find the value we're looking in left, we only have to do that once. And and left plus right can be at most n. So then that's just time O of n, right? We look at most O of n elements because there's O of n slots on the plank, and left and right can't be on the same value, so they can't double there. And there's no repeat, so you can't have like a million, you know, ants on one slot that we have to look at each individual one. So it's still less than n. That's all to say, you know, the length of left plus the length of right is less than or equal to n. So then we don't need to think about this in terms of left and right. Okay, rambling too much. All right, everybody, peace out.